Hello everyone and welcome to today's webinar, Motors 101, Learn the Basics of Electric Motors. Before we get started, I'd like to go over a few items so you know how to participate in today's event. You've joined the presentation using your computer speaker system by default. If you'd prefer to join over the telephone, just select Phone in the audio pane and the dial-in information will be displayed. You will have the opportunity to submit text questions to today's presenters by typing your questions into the questions pane of the control panel. You may send in your questions at any time during the presentation. We will collect these and address them during the Q&A session at the end of today's presentation. Today's webinar is being recorded and you will receive a follow-up email within 24 to 48 hours with a link to view the recording. I'd now like to introduce Kevin Shepard, Director of Texas Business Unit at Ward Leonard.
All right, good morning, everyone, and thank you for taking the time to join us today on our first webinar that we're putting out. This topic is really just designed to be very high level and overview of motors in general and the components. Really to just get a basic understanding of how and why motors are used and how they're applied. So we'll get into some of the nuts and bolts of it, but not too deep. A little bit about myself. As you can see on the screen, I have been in the electromechanical repair business for a long time. Really have just kind of come up through the shop and worked my way into sales and then operational management. So have had a lot of experiences on the different types of motors and the evolution of motors, the application of motors, why motors work well, why they don't work well. Don't know if that makes me a super expert on what we're going to talk about, but I do know enough to be really, really dangerous. After that, we'll go through an overview of Ward Leonard and just kind of give you a high-level perspective of our company and the different products and services that we offer. Then we'll go through the presentation, and at the very end of it, we'll have a Q&A and leave a little bit of time for questions. Okay. So let's just jump right into it. So this is our company. Ward Leonard is a company that's based in Connecticut. That is our corporate headquarters and also our manufacturing facility. We do have two other operational facilities, one in Houma, Louisiana, and the other in Houston, Texas, which is where I'm located. The Louisiana and Texas facilities are more focused on the electromechanical service sector as far as repair of generators, repair of motors, repair of land-based drilling apparatus, those types of things. So definitely motor-related facilities in those two locations. Ward Leonard, Connecticut is more of a manufacturing facility where we do manufacture our own motors for the Department of Defense. We do it for the drill market. We do it for generators and other things. So that's really where the Connecticut operation comes in and helps to support the other two facilities. So we're very broadly spread in what we do. Our reach goes into a lot of different industries. So if you're looking at the markets that we cover, definitely heavy into industrial, as far as processing plants, power generation, chemical, marine, offshore, on and on. Anything that really deploys anything that deploys electromechanical apparatus, we're pretty much involved in that. Oil and gas, all the different methods of obtaining oil and gas and moving it around. So upstream, midstream, downstream, and even into fracking. We do have some influence into that. Very proud of our military input and support into our naval fleets. We have had a long history with the Navy, I should say, and been supplying them parts and materials to help support those vessels as they go out and defend our country. So very, very proud of that business that we're in. And then ultimately at the end of it, service and repair, which is what we're going to really talk a little bit about today and the apparatus that's contained within that. So in-shop services, we do that, basically available 24/7. Our field service team is a team that is globally deployed. So we can pick up and go anywhere and do just about anything as far as related to controls, motor repair, motor assessment, electrical signature analysis, current signature analysis, vibration analysis. We can do turnkey installations, very broad offering in service and repair. So that is ultimately available to you. And if you need anything in that regards from any of these areas that we're in, we're certainly more than happy to help in any way that we can to help support your plant. All right, moving on. So why electric motors? And this is a good slide to really start with because it really does kind of set the stage for why there's electric motors, why there's such voodoo in it. I mean, by voodoo meaning a lot of people either don't understand the scope and application of motors, how they work, what it's doing. When you talk about electric motors to people maybe who are outside of the industry, they immediately go to a Tesla car, which is true. I mean, it's all driven by electric motors. But electric motors are literally everywhere. They are in pumps and air handling, conveyors, appliances. You think about your air conditioner, your refrigerator, an air compressor. A lot of things that you would have just around your house have electric motors in there. And really, it is just it's a transformation of energy into work, and it's really a very safe way to convert that electrical energy into mechanical energy. In a combustion type of an engine, you have noise, you have heat, you have emissions, you have a lot of different things that don't make a mechanical engine very applicable, right, to a lot of situations where an electric motor comes in and does that. I mean, as an example, you can't really put a diesel engine out inside of an environment that has a high potential for either gas, combustible dust, anything like that that could potentially cause an explosion. That would be not a good place to put an engine. So that's where motors come in and they're relatively safe, right? So when you look at all the power that's generated across the world, motors consume about 60% of that power that's generated. So that is also why in our industry, we talk a lot about efficiency, a lot about conductors and insulation and the design of motors and air gap and slip and torque and other things that really help to mitigate that consumption of energy, right? There's over, gosh, the course of my career, when you had a general purpose motor, if you were 80% efficient, you were doing pretty good. You're talking about old U-frame motors, and I know I'm dating myself when I say U-frame motor, but it is back in that day. These things were massive, and they consumed a bunch of energy. Now, you get a lot of horsepower, much smaller package, which has, and we'll talk about this in the next few slides, but it's really materials based, and the progression of insulation as materials have been discovered and applied to keep energy inside the conductor, right? And that becomes more reliable, right? And the consequence of that is, hey, you get to put more energy in a much smaller package, right? Because you're not worried about it going to ground. So we'll move on. So what we're going to do is walk through the different frame or the components of a standard motor. And I know this is really high level, and this is just kind of where we're starting. That's why it's Motors 101. So, but we will break down these components some. And, but a standard, and what we're looking at right here in this cutaway is a standard AC induction type of a motor. Just the basic run of the mill, out of the box. Here you go. Apply whatever voltage to it, mount it, and let her go. This would be probably the most common type of motor in the industry. And so we'll talk about the frame, which let me get my pointer up here. I think we can do that. Yeah, here we go. All right. All right, so everybody should see a laser pointer. Okay, so the frame would be this material around it. So the frame is what holds or contains all of the components. So when you talk about the motor frame, it is everything. So the foot, the shaft, the housing, the type of cooling, the terminal box, all of this stuff goes into frame. So when we talk about motor frame, we're dimensionally saying this is the size of the motor, and this is the bolt holes, this is the shaft size, this is the length of the shaft, this is the height of the shaft from the feet, so that's frame. We talk about the stator. The stator is the inside of this. The stator really contains the conductor, and then the rotor would be the rotating elements. That's going to be the mechanical output of the motor. Okay. So we can get the next slide. Next slide, please. All right, so right now we're going to put a poll up, and what this does is in the poll question, it really just kind of gives me an understanding and helps us to really gauge where you guys are at in your knowledge base of electric motors. You know, this, like I said, this is a very high level type of a thing, but just take this time right now to go ahead and answer that question, and then I will share the results with you on, you know, what the level of experience is with our audience. We have about 19 attendees on, so just go ahead and take a second if you would and answer this, and lets us know where you're at. All right. Okay, so the results are in, and for the majority of you, more than 5 years of experience with electric motors. Looks like 50% of you responded with more than 5 years. Had 20% with a year or less, 10% with 3 years or less, 20% 5 years or less, 50% of more than 5 years. So we do have a pretty good spread of people. You know, for you guys that are a little more, I guess, experienced in electric motors in general, then this may be something you already know, but turn this off so I can advance the slide. But we'll go through it anyway, and then hopefully you'll get a little bit out of it. So let's talk about frames. The frame is the component that I think has the most flexibility to it. And what I mean by flexibility, it is all over the place, right? So in a cast iron frame, which was kind of what we looked at in the first slide, and it really does have a shows this picture right here. So this cast iron type of configuration, very common, right? Totally enclosed, fan cooled. So you can see the cooling vents. There is open drip proof, which would be a different type of design where you really wouldn't have these cooling fins on the outside. It's going to be a smooth body motor, but the bottom of it is going to be open. So if you had and really the whole design of these is to get rid of heat. So that's why you have these cooling fins. Fan goes on the back, blows across the cooling fin and cools the motor. Obviously, if you have a motor that has an open bottom design, then the cutaways on the motor really do allow for better cooling. So if you got an indoor application that's got pretty decent ambient conditions, open drip proof, more than likely your best bet if you're looking to get higher efficiency out of your motor. Right? They're smaller. They're you know, just don't take up so much room. That's not always applicable, right? So that's why you have the difference. In a cast iron frame, we usually see these in up to about 2,500 horsepower. That's about the max that you can get when you do sand casting of a frame. When it gets larger than that, it just becomes really difficult, and you're talking about cost to manufacture. So it just doesn't make a whole lot of sense to build anything in a cast type of configuration that's much larger than 2,500 horsepower. Shaft height about 24.5 inches is about the typical largest thing that you'll see in a cast iron type of a frame. Anything larger than that would be in this picture on the right, and that's when we go into fabricated steel frames. So plate steel is cut, all welded together. This gives the manufacturer, the OEM, the ability to custom design pretty much any footprint that you would like. There's not a whole lot of restriction in what you can build. And as a matter of fact, we're now starting to see induction type motors definitely up into the 100,000 horsepower range. Seems like induction in general, with the controls and the advances of that, are replacing some synchronous applications. So the induction motors are definitely getting much, much larger than what they used to be. A lot of that has to do with energy efficiency, reliability, cost of maintenance, operating cycle, those things. But it's basically the difference in the frame. The frame is really important because it's going to hold and contain all of the conductors, all of the steel laminations, all of the things that really do apply magnetic force to the rotor and make it go around. So we have to have that. So this picture right here is a picture of a stator core that has been removed from the inside of the stator frame, right? So that's basically the component that stays in there. The rotor, I mean, if you want to have an easy way to remember the difference between the two, stator would equal stationary, rotor would equal rotating. So this graphic right here is showing how magnetic force is applied to the rotor. And what you mean by magnetic force, it's very similar if you ever play with magnets. When you have opposing poles, a north and a south, they will attract to each other. If you put a north and a north together, they oppose and then they push away. So basically magnet wire, ground conductor, solid conductor, any of the copper wire that's in there, why it's called magnet wire is it's because it's carrying a current through this stator core, which is creating a magnetic field that then rotates around, right? At 60 cycles per second. That would be, in the United States, that's our frequency that we work with. Over in Europe, it's 50 cycles per second. It's a little different, but still, it's a rotating field. And so you have a north, south, north, south, north, south, and that rotates, which then pulls this rotor along with it. Right, that's why air gap is so important, because the tighter that gap is between that rotor and that pole piece, the less slip that you have and the more efficient that you'll get, because it just doesn't have to create as much magnetic energy. Okay. Laminations that really is honestly where all of the magic really happens inside of a motor. So the conductor, and we talk about slot design, slot width, slot geometry, insulation that goes in, it all goes in right through here, right? So this would be a lamination section. They're called laminations, and it really has to do with the fact that each piece of lamination is then sandwiched or connected to the other one, but they're electrically insulated, right? That's really important, because what you're doing is the conductor goes through the slot, right, and then makes a turn, and that's called a span. So whatever the width of that is, can be 1 to 12, 1 to 14. We've even seen some 1 to 13 and different. Everything's a little different. But anyway, that goes in, creates a pole, and then it excites this metal and creates a magnetic field. And then that magnetic field rotates, and then that's what pulls the rotor around. So and as I said, the individual steel it's insulated from each other. When we talk about core loss, we talk about having to burn out a motor on the repair side of things, which is what we do. We do repair motors, so we will take your failed winding, pull the old copper out, re-insulate it, or actually replace the copper, re-insulate it with new materials, insert it, and rewind it. One of the things that we have to make sure that's absolutely correct is the core plate. And it's a statement down there about using the proper temperatures to burn out motors, and because you really do have to kind of incinerate the insulation package, and then that's how you remove the copper out of the winding or out of the stator. But it is critically important that those laminations of steel are not shorted together. If it is, it creates a hot spot. It will be an electrical short. So how we check for that is through core loss. So we have a machine similar to a welding machine, but probably a little bit more current, and we throw a cable through the center of that. It creates a magnetic field that excites the stator frame, and then we take a thermal camera and we start to take images of the stator core. And what we do, if there's a short in there, it will show up as a hotspot. And if the hotspots are too bad, then we have to replace all these laminations, which is called a restack. So we'll pull all this out, have new laminations made, restack it all in there, rebuild this entire stator core, and away you go. Sometimes these can be corrected just, literally with like a rubber mallet. You go in and just kind of whack it really hard, and they just spring apart because they just get stuck together. So that shock will take them apart. So there's a few different ways to do that, but the critical thing if you don't have it in your repair specification and you're dealing with a motor shop for repair, make sure that you understand exactly what temperature they're burning your stators at. There's typically in North America, we use C5 materials, a C5 core plate, which is a little bit better steel than what we've seen either previously, which would be C3 core plate, or even some of the stuff that's used in the Asian manufacturers and some of the cheaper motors. I mean, that's where they really get, when you got kind of a well-known brand, whether it be Siemens, ABB, Baldor, WEG, any of those guys, they're going to use a little better materials. And the core plate is expensive. When you see other things, and I'm not going to knock on anybody's product, but who the low price options are out there, more than likely this is where they get a little bit of cost savings. They will use C3 core plate. They will use laminated insulating materials, Dacron, Mylar, Dacron. They will use just different things, a little cheaper lead wire, some things like that. So you can definitely get them cheaped up if that's what you want. But anyway, the effect on that is C3 core plate. Every time you burn it, that core plate absolutely decays, and you get to a point where you are not able to repair that motor any longer. On a C5 core plate, with a shop that knows what they're doing and burns the motor correctly and strips it correctly, you really shouldn't have any sort of efficiency loss or materials damage to where that the motor could not be rewound again if it were to fail sometime in the future. That is why it's really important to partner and collaborate with your repair facility on how they are repairing your motor, and make sure that you're comfortable with their process and that it lines up with something like this. You never really want to go above 700 degrees F. I mean, I would rather take it a little less temperature and just have a longer burn cycle, honestly, than take a risk of flashing that over. 700 degrees is really, really hot on the lamination. So okay. Talk about the stator coils a little bit. There's really two different types. Not really a lot different. There's different types when you get into different motors. I mean, obviously in DC motors it's different, but really the conductors are going to be very similar. So you're going to have a random wound or a mush winding, and this would be the most common in the standard sizes of motors that you see, like the smaller T-frame type of motor is going to be a random winding. And really why they call it random, it's just because the conductors, and you see that it's like group of single conductor wires that a winder is going to make that coil himself. Like most of the repair shops that do this type of a repair are going to make that coil in-house. It's all drawn for, say, number 16 wire. You got 12 wires in hand, meaning that you're pulling 12 wires simultaneously out of buckets, and then you're going on a winding machine that then coils this all together to give you your span width, which we talked about that before. That's the difference in when you put one, or what would be the bottom of the slot, or the bottom of one coil and the top of another. That's the span. And then the links on your end turns. So think about a conductor. Electricity goes in, makes turn, comes back out, and just makes this continuous loop, and then works its way around. So that would be how much windings or random windings work. How we do it at Ward Leonard is we have a automatic coil winding machine. Basically, it is a computerized machine that we go in and program in all of our geometry for the coil. So we're going to dictate this is what our span is. This is the coil width we need. This is what the end turns will look like. This is how many turns I need. This is how many wires I'm pulling. And the winding machine has a automatic tensioner on it that we can set the tension so we get a good, nice, tight coil. And then we also go through the difference in these two is you have a concentric head, which is just kind of like a big oval. And then you have a diamond shaped head, which kind of like little triangles on either end of the coil. The advantage to diamond shape is that the coils tend to lay on top of each other better. Whereas if it's a concentric coil, you kind of have to beat them into place. When I say beat, that's the winders would kill me for saying that. You have to form them into place. So there's a lot of shaping of the coils on a random type of a concentric type of a head. Diamond head, a little more complicated setup, much better finished product, and really the rewind goes a lot quicker because you don't have to shape it. The less you have to move these coils around, the better. Each one of these windings or the copper conductor, it has a coating on it. They're insulated from each other. If you didn't have that insulation on that, or if you nicked it, or you cut it when it was being shaped up, then you would get what we call a turn-to-turn short, and your motor would fail pretty quick. Right? So short circuits are bad. You can't have those. That's why it's really good to protect all the conductors, and you see all of the insulation that kind of goes in this thing. Right? So that coil is now laying on top of another coil. This has all been wrapped and insulated. Lots and lots of insulation on the end turns. The slots are all insulated because we really can't have anything go to ground. So that's where your liners, your top sticks, all those things go in to help keep the energy inside the conductor. On the form wound side, which is what we see typically in voltages 2300 volts and greater, this is a coil that is usually, can't say this for everybody, but usually most repair shops buy this coil from a vendor. Your better repair shops do have their own specification for the coil design, for the type of insulation that's being used, whether that be any enamel. Typically you start with a conductor, which is enamel coated flat or rectangular wire. And then there's glass, which is basically fiberglass or Dacron. That conductor is then wrapped in glass. We call that glass over film, right? And then that conductor is then formed into this coil. And then the white material on that is usually, for Ward Leonard, it's going to be Nomex. That's our spec. We rewind with pure Nomex and non-laminar slot fillers and top sticks. So all of our top sticks are fully phenolic G10 or better glass, right? So when you see this white insulation, and just because it's white doesn't mean that it's Nomex. I mean, there's a lot of other tapes out there that are different. But for us, we use Nomex, and the reason we use Nomex in a full Nomex system is it gives us a consistent Class H design. So as far as temperature rise goes, we are better than the OEM build typically. OEMs have aligned, for the most part, I mean, you can spec something differently, but for the most part, they have all aligned on a Class F type of insulation, which is fine. It's just a little cheaper and it's a little bit more attainable. Most of the repair shops use Class H, the systems. You just get a little bit more temp rise out of it. And when you're talking about having to warranty your product, and if you're a reputable shop, you are definitely putting a warranty for parts and materials on your product before you lease it back out to the customer or the end user to be installed. It just mitigates a lot of risk, right? So we want to put the best materials that we can in there, so that when we give you the repair back, we're highly confident this thing is going to function as advertised and it's going to be reliable, and that we won't see this motor again for 40 years. That is what we feel is the life of our rewind is about a 40-year life cycle, right? So the advantage to Nomex over some of the laminar winding materials that you'll see in other other situations is that, let's say you have a laminated DMD, Dacron Mylar Dacron, and it's a Class F design. You over temp it, which can happen, especially down in Texas. It gets hot here and humid, and you're running into the service factor and. So all these operating parameters just really make it a difficult thing for the motor to run. So let's just say at some point the motor overloads briefly, over temperature, something like that. You actually have a flashover of the insulation system that then the laminations then separate, and it now doesn't retain the same electrical insulating properties that it once had. It can't return back to its original form because it's been damaged. It's been over-temped, right? Been burnt. Nomex is not like that. Nomex is a system that has the flexibility, as long as you don't exceed the Class H rating for an extended period of time, but you can exceed Class H for a limited period of time. But you can go into that higher temperature range. It can absorb the heat. When the motor cools down and normalizes, the insulation material in Nomex will return to normal as well. It will normalize, right? So it has the ability to flex temperature over, temperature under, temperature over, temperature under. Think about the temperature swings we get in Texas when you start a day and it can be 80 degrees, and by 1 o'clock in the afternoon it's 100 degrees and we're all dying, right? So the motors are going to experience that too. That's the advantage of those systems and why it's different, and really why we at Word Learner use that Nomex, full Nomex system. The top sticks and the materials that go in there are all really important. It needs to be robust. It needs to be able to handle torsional forces and rotating elements. This is a very clean winding right now. It's new, but as these things operate, over on this side of the winding is where all of the mechanical apparatus is. So you've got oil, dust, heat. You get migration of insects, varmints, snakes, lizards. I mean, you name it, get it all. Everything finds its way into that motor. Sometimes, I mean, if it's totally sealed motor too, we don't know how stuff gets in there, but it just does. So that is why all these materials that are used to hold the sticks or to hold the coil in place really do matter, right? You don't want to go cheap on that stuff. Okay, move on. We talk about, this is where the coils are inserted into the laminations and into the slot, and the tapes and the insulating materials differ as the coil comes out of the slot and into the end turn, right? You can see here that we have some extra protection as the coil is coming out of the slot and into its end turn, and then it's going to come around and return back into the slot, make a full circuit. Why? And this could be gradient tape, this could be armor tape, this could be conductive, this Corona tape if it's a high voltage system. It could be a lot of different things. The reason why we do that is because the exit of this coil out of this slot, all a conductor is doing is keeping the energy inside of it as it circulates through. That voltage absolutely wants to escape, wants to come out and go to ground. So as voltage and current are being pushed through, the voltage and current definitely want to jump out at this point and go to ground. That's just the easiest place for it to do it. So we have to apply a little extra protection there. That's worth noting. So when you see the coils, if you've ever been in a motor shop and you see the difference in coils, that's why that is the way that is. It's the different tapes do different things, right? And in this picture right here, it is showing when a coil is inserted how much care goes in. So that's a piece of Nomex right there, and the coil is laying on the inside of it. The winder is going to insert and push that coil down into the slot, and that Nomex is there as a liner to really just to protect the tape. It doesn't do a whole lot other than that, but it really is there designed to protect the rewind process when the coil is inserted. All right, and then finished product over here. What you want to look for in your rewinds more than anything is symmetry. And what I mean by that is the coil spacing on these end turns, because the slot is going to be the slot. It's really dictating, how the coil lays in. It's segmented and separated. It just is what it is. It's a mechanical type of a fit. The coil goes in, it's got this much of a measurement, fits in this slot. It was specifically designed for that. Boom, there you go. But out on these end turns, it's really where you see the quality of a rebuild. You want to look for mechanical bracing. You want to look for blocking and felt placement. Coil geometry, meaning the spacing between each coil is consistent all the way around. There's two things that do. Number one, first and foremost, it just speaks to the quality of the rewind job when you see consistency and uniformity in the rewind. There are absolutely lazy people out there who just don't take the time to shape these up and space them correctly. And I don't know, if I see something like that, to me, it really speaks to the quality of the entire build. It just does. I'm a stickler for having uniformity of the rewind. The other thing it does, which is probably even more important than just my OCD on rewind uniformity, is that you really need to have that spacing correct because of the electrical signature that it produces as the voltage moves through and transitions around the winding, and then also for cooling, right? Think about it. So if these two coils are tight here and I can't get air to pass through, I'm not getting any cooling on that segment, right? I'm just not. So it's going to run hot. Potentially, over time, I would say that your potential for failure is greatly increased just because you don't have the correct gapping, right? So there's a lot of things that can happen and why it gets that way. And even on the when we talk about the random windings, the mush windings, even that it needs to be shaped up correctly for cooling purposes, and really for the healthiness and the reliability and longevity of the conductor. That's really why you do it. This down here shows some surge rings that are placed on a winding, right? So right there. You've heard of surge rope, maybe not, but if you haven't, or you have, surge rope is really there in order to hold these end turns down and in place. And that is important because you talk about inrush current. So when the motor is started from a stop, a motor just wants to get motors just in general are they just have no intelligence to them. It's just a basic conductor. Think about an empty glass that wants to get full as fast as it can. Right, so you just dump as much water into as you can, and it just starts to soak it up. A motor's similar to that, so it just dumps in as much energy as it can, and as it's doing that, you're talking about current. So voltage goes in, voltage is going to be consistent, but the motor's trying to draw in as much current and energy as it can at one time to get going as quickly as it can. So the current just spikes, and you're talking about a massive spike in current that happens over a short period of time. But anyway, we have to protect the coils with that because we will get mechanical movement from these coils if they're not braced properly. That's why all of your bracing, all of your surge ropes, all of the blocking, the materials to use, all super important, because you don't want these coils to flex during startup, and really even during operation, just through vibration and stuff like that. But most of the time it's during startup. Why? If you think about taking a piece of metal and you bend it back and forth, right? Over time, that back and forth bending is going to fracture the metal and it's going to break. So we do see, and you're talking about really fine layers of mica that that's the insulating properties in the tape. That's really what does all of the insulating is mica, which is basically a rock. It's a mineral. And that it's not really the conductor you're worried about breaking, it's the mica, it's the insulation, because that will just, and then it'll just break and crack. And next thing you know, you got to turn short, and it's bad. Then we'll see your motor again in my repair shop. So bracing is really important. That's what that's showing right there. This is an interesting picture of a water submersion test. The motors at Ward Leonard have the capability to go through an IEEE spec water submersion bath. So, and what that's designed to do is just, I think that's pretty much the ultimate test of if you have a good installation system or not. It's just energize it and dunk it in water. So we do a fully energized high pot test while the water is submerged, or while the motor is submerged in water, leave it there for 4 hours and then monitor the results. That is a part of our quality policy. That's how we know if we have a good installation system or not, if it's going to pass. So we certainly can do that for your motors as well. And if your motor shop, whoever you're using, is not willing to do that test, I would consider the value that they're providing you, because if you have a good installation system and all the things that I just said were done correctly, you should be able to submerge that motor in water and it pass. Not a problem. All right, VPI is vacuum pressure impregnation, and really how this system works. It's designed to cure the formed coils, right? So it is vacuum pressure impregnation. So there's two cycles to it. There's a wet vacuum and a wet pressure. There's a dry vacuum and a dry pressure. That is the cycles that it goes through. So this is a picture of a VPI tank and a stator going into it. It's a completely wound stator. So after everything is wound and everything is put in there, you need to cure the coils, which means we need to put resin inside of the coils to make them hard. The resin is designed to work with the tapes so that it flows inside of the tapes, passes through all the mica and into the coil, into the conductor, and then you get an epoxy filled coil that becomes very, very hard. So now you think back about why we have to burn out a motor. It's because of this. It's because you have to get this epoxy, and the epoxy systems are so good. There's no other way to get that coil out of the slot unless you burn it. So motor is going into the VPI tank. This is essentially a vacuum chamber is what it is. So before the motor goes in, the chamber is filled with epoxy, which then goes over the top of the motor. Let's see if I can get the pointer here. So it's got to cover the top of the winding. The winding has to be fully submerged in epoxy product, and you can be here. Some people call it varnish. It just depends on what you're using. At Ward Leonard, we use a Von Roll product. It's called 74035T, and the T is for thixotropic. It's a pure solids epoxy, meaning that we don't have any petroleum thinners in it. It's just a different system. For us, it works. It's designed to work with our tapes. It's designed to work with the process that we have, lead wire, surge rope, all that stuff. So it's a homogeneous type of a system, meaning that every component that we use is designed to work together. If you have dissimilar products, like if you're getting your tapes from one place, if you're getting your lead wire from another place, if you're getting your sticks from someplace else, if you're using non-compatible tapes, if you don't have the mica content right in the tape, you will not get full penetration from your VPI, and you will have voids and air pockets and basically bare conductor type of wire in your rewind, and that can lead to partial discharge issues. That can lead to definitely hot spots. That can lead to electrical vibration, which will be picked up in actual mechanical vibration as you get the rotor rotates and pull pass frequency occurs. As that pull passes a loose coil, it will vibrate, and you'll see that in mechanical vibration. Right, so you can definitely have an electrical issue that causes mechanical vibration, and that's how it happens. So really super important that all of your components are designed to work together. The VPI process, which is kind of a long process to go through for the stator, but that's the one you want to get right. It's usually about a 12 to 14 hour process. So it fully submerges into VPI material. So it goes into the epoxy, gets pulled under vacuum, which basically sucks all of the material out of the tank along with the air. We're trying to get the air down too, so we pull this thing under such a deep vacuum, just try to get all that air squeezed out of that tank. And then it stays there for about 6 to 8 hours, and then we reverse it, right? So then we push pressure back into the tank. So we're actually pulling air out and then pushing material back in the tank. So, through that, we hope to then have removed any air bubbles, any voids, any pockets, because we want that coil just to be so tight in that slot. And if you get it just right, mitigate your PD, you increase mechanical rigidity, and all is right with the rewind world. Okay. Sorry. Okay. Different motor types. AC induction squirrel cage, most common. Absolutely, that's what we just looked at. On the first slide. It really simple, really basic. It's called a squirrel cage really because the design of the rotor looks similar to a cage in a mouse cage or something the squirrel would run around in. So maybe 8 different components on it: 2 end bells, 2 bearings, rotor, maybe rotor caps, stator frame. Very easy. AC permanent magnet. These are a little different. That's when we say probably the motor of the future, and the reason that you say that is because most of your electric cars and anything, you think about how many, they've even got skateboards now and bicycles that have electric motors and electric motor driven. It's all permanent magnet design, right? You get a lot more torque out of a very, very small package, and really just really quite reliable. There's just not a lot of stuff to go wrong in them. And you don't need as much magnet wire. You don't need as much conductor in there, because it's just like the rotor has magnets on it, and so the rotor just kind of does a lot of the work there. So the winding basically creates a magnetic field that rotates, and the rotor does most of the work. Wound rotor, you may or may not have these. This is still a design that's out there. Very high torque stuff. The rotor, instead of having magnets on it, has magnet wire. So it is mechanically, or actually maintenance-wise, there's a little bit more to deal with there. But high torque, you can control the speed on it. Where you see slip ring motors in a lot of places, was in a lot of large hoists, overhead cranes, any kind of crusher motor that has to have high torque. We're talking about older wastewater treatment plants, and it was that because in a wastewater treatment, the viscosity of the fluid changes, right? So you have to be able to have a torque variation. That's what it is. Synchronous motors. A lot of the larger plants out there definitely have synchronous, and it's a design that provides a lot of torque at a very slow speed. So if you're thinking about a large reciprocating compressor, if you need a mass amount of air, if you're doing, in whatever process that you're doing in your refinery, a synchronous motor is a great application for that. Slow speed, some of them are high speed. It just depends on what you want. We've seen stuff as low as 200 RPM, right? That's, 1,500, 1,800 horsepower, 2,000 horsepower. Something that slow is going to be a really, really big motor. It takes a lot of copper to slow a motor down. The improvement in power factor, this statement right here, that's one of the benefits of a synchronous motor. And as we kind of go through Motors 101, there's more to the deck that's really what we're talking about here. But and we can get into that in future conversations with Motors 101. But one of the benefits of a synchronous motor is that you can stabilize power factor, right? You have the ability to control power factor, and if you have a plant that operates on a multitude of, and more than likely you just have a main bus system coming in with a motor control center that is operating 30, 40, 100 motors. I don't know, it just depends on how big your bus line is. But as those motors kick on and off, and as load varies and transitions, you will start to see power factor spikes, kind of moves all over the place. And because you get what we call a highly inductive line, because we talked about earlier, when that motor turns on, all it wants to do is draw as much current as it possibly can to get it going and up to its operating speed as quickly as it can. So you have this massive spike of inrush current, which affects your power factor, right? So a synchronous motor, you can lead or lag the phase angle. Well, it's getting kind of technical, but that's basically what it does. You have the ability to manipulate phase angle. And then you can offset a highly inductive circuit. So one of the benefits of a synchronous motor is it just makes your power so much cleaner. And motors love clean, pretty power, just like people like to eat really nice, good food. Motors are no different. They want really clean, nice, consistent power. Okay, so that's the advantage of a synchronous. And then a DC motor. These have been around really forever. Our company, Ward Leonard, the guy that founded it, Ward Leonard, really, we were one of the initial inventors of a DC motor controller, very similar to a rheostat, but that's kind of how we got into this whole business. Gosh, 128 years ago, like a long time ago, we've been doing this. So DC motors, they're used in the oil field pretty prevalently in the GE 752 design. They're also in steel mills and paper mills, and really because you have the ability to vary speed but hold torque constant. Now think about if you are in a paper mill or a steel mill and you have a reel that's empty, right? The reel weighs whatever it's going to weigh when it's empty, but as you're filling that with your product, weight's going to go up, right? So the weight is going to increase, which if you increase weight means you also increase load. So that is a different torque requirement, right? So you need the constant torque, but you also need to vary the speed as the spool fills, right? So that's where a DC motor really comes in and does its magic. There's a lot of stuff that goes into DC motors with commutators and brushes and brush design and, just getting that thing right. But they're definitely still out there and definitely the workhorse of some of these applications. So I was trying to get a little quick. I kept looking at my clock here and just making sure that we left about 10 minutes for questions. So we left about 8 minutes for questions, but that's going to conclude what I've presented. I know there was a lot of material in here. Hopefully I didn't chop it up too much and you guys got something out of it, at least understand the basic components and designs of motors. But at this point, we'd open it up to questions if you have any. So I'll just wait and listen.
Thank you, Kevin. So we're now going to begin answering the questions submitted during today's presentation. As a reminder, you can still submit questions through the question pane in your attendee control panel. So Kevin, we have a few submitted already, and our first one here is, how do I decide what motor to use for what application?
That's a really good question. And that's not a really easy answer. And really it's your motor shop or your service provider, whoever that is, who's ever going to sell you that motor really needs to understand what the application is, what the environment that you're installing it is, what you're trying to get out of it. Do you need constant horsepower? Do you need constant torque? What's the right enclosure? What's your voltage? What's your operating requirement as far as time cycles? What type of a service factor do you need? Meaning, does the motor have the ability to overcurrent at times? That's where service factor comes in, where you can run the motor a little hotter or harder than what it's supposed to be. There's not really a super easy answer to that question other than whoever is you're partnering with to buy the motor from, whatever, or just engineer the design, really needs to start understanding what your need and requirement is. And that's really the best answer I can give you.
Great, thank you. So our next question is, in school, I thought we learned the real issue with lamination was removing or reducing eddy currents, or is the heat a result of the eddy current?
The heat is a result of the eddy current. That's exactly right. The lamination and the type of laminations and the really the insulation between the two laminations is what's going to accomplish that. But when you do get core loss, it is a direct effect of eddy currents being applied to the lamination, and that's when you see, or it can actually be ambient conditions too. You just see rust. The coating on the steel just kind of rusts away or whatever. But yeah,
Okay, thank you. So next we have, what's the most important maintenance that should be performed on a motor to prevent breakdowns?
Um, Really, for if you talk about what we see the most in the shop, the number one cause of your unplanned and unscheduled maintenance or breakdown would be mechanical maintenance. You have to take care of your bearings. You have to take care of your lubrication systems. Very close second to that would be the alignment of the motor. And that could be either the base integrity, if it had soft foot, if you had a coupling that was wearing, if you had linear loads, if you had vibration, harmonic issues, anything like that that's going to cause mechanical wear. Typically, if you get the winding right, and the winding isn't exposed to a lot of moisture and heat, the winding's going to last for a long time. Where we see a lot of failure is on the mechanical side of things. So bearings and bearing maintenance really super critical, and then keeping your motor clean and cool. And that's why, probably depending on how often the motor operates, maybe every 5 to 7 years, you'd want to pull that motor out, send it in the shop, have the mechanics gone through as far as getting it rebearinged, or if it's a sleeve type of bearing, have the sleeve bearing redone, get the oil changed, and then we would clean everything and uh, steam clean all the windings to make sure that there's no buildup of material on the winding to keep it from getting cool.
Okay, great. I think we have time to take a couple more. So what's the most common cause of motor failure?
Um, for us, what we see most commonly, honestly, is probably mechanical failure, bearing failure. That's more prevalent, I think, than just about anything. You will see there are instances where you have windings that fail that then take the motor out. I think it's a little bit more rare. Just because if it's a newer type of a motor, the insulation systems that go into the motors now are so good, they really don't factor in it too much. However, you still have lightning strikes, you have surges, you have improper cooling of the motor, you have things that will absolutely take the winding out. But I think largely what we see most is either improper greasing, that's either under greasing or over greasing. Over greasing really bad, because you can actually apply a preload to the bearing, meaning that the grease is too much resistance on the bearing, so the bearing experiences um, a mechanical resistance just trying to move through the grease. And if you have too much of a pressure on the bearing overheats, and then if it overheats, then it cooks out all the lubrication, and you wind up wrecking the bearing anyway. Overgreasing really, really bad for motors. Yeah.
Okay. All right. So what size range of motors does Ward Leonard work on? And more specifically, do you work on high voltage?
We do work on high voltage. We have a specific system that we use. Um, we can do talk about sizes of motors. I mean, it really just depends on I think what the motor application is. I mean, I can't say that we can work on a 100,000 horsepower motor. We certainly can. I don't know that we can fit that in the shop. I don't know there's a lot of people that can fit a 100,000 horsepower motor in the shop, but there's a lot of things we can do in the field. Like in the shop, I would say that 15,000 horsepower would be about what we can do. Um, we do have 50-ton crane capability, so certainly material handling not an issue for us. But where most shops are going to run into the issue, especially on large motors, is on a rewind specifically, is what can you fit into your tank? And for us, that's right around 5 to 7,000 horsepower is what will go into our tank. We've got a 12-foot tank, I'm sorry, 10-foot tank here in Houston, so we can get a lot of big motors inside of a 10-foot tank. But then after that, then we go with different strategies as far as if we need to go to a hard coil, something that's B staged, and that's getting a whole nother conversation. But um, if you have something big, give us a call. We will absolutely figure it out. We're not afraid to work on big motors.
Thank you. And I know we're short on time. I just want to squeeze this last question in. So, do you guys offer field service to analyze a motor on site?
We do. And as a matter of fact, our field service group, uh, very highly equipped and educated and very technically capable to understand mechanically what's going on with your motor and electrically what's going on with your motor and to do diagnostics. So if you're having a motor issue, we have a lot of resources that we can deploy to go help understand exactly what that is. We do our preferred method for motor diagnostics is PDMA. Uh, you know, all of the techs have their own PDMA tester. Everybody's trained on it. We PDMA test every motor that comes through the shop. So we're looking at we are looking at the electrical signature analysis and the current signature analysis. Right? Those are different. Then we can also go out and look from a vibration analysis perspective, take sample data, go back and look and see mechanically what issues are going on with that. You know, we also do trend analysis as well. To me, that's the best way if you're creating a maintenance reliability program. You have to trend that out. You're gonna have a baseline and then look for changes over time. That really gives us a good indicator of how well your motor's operating and how long we can expect to have the motor operate reliably.
Thank you so much, Kevin. And that is all of the questions that we have today. So, with that, on behalf of Ward Leonard and our presenters, thank you for joining us today and have a great rest of your day.
Thank you, everybody.